We have a problem here that asks us how many of the following molecules are polar, and we are given 5 different molecules. We should approach this problem by drawing the Lewis structure for each molecule, determining the molecular geometry, and determining if there is a net dipole. A net dipole would mean that the molecule is polar, and no net dipole would mean that the molecule is nonpolar. Let's start by drawing the Lewis structure for SO3. S is going to be our center atom, and we will have 3 oxygen atoms centered around it, and we will have a bond to each of those oxygen atoms. We need to go to the periodic table and determine how many valence electrons will be in this molecule. I've determined that there will be 24. We need to start by giving the outside atoms, which are all the oxygen atoms, octets. So now that all of our outside atoms have octets, let's now see how many valence electrons we will have left, or if we have used them all. I'm going to count by pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 pairs of electrons gives us the 24 valence electrons that we were looking for. Let's now draw the molecular geometry for this molecule. This molecule has 1, 2, 3 domains. So it will be a trigonal planar molecular geometry. There are no non-bonding pairs on this molecule. The oxygen atoms will have partial negative charges because oxygen is more electronegative than sulfur, and the sulfur will be given a partial positive charge. The dipoles will move towards the oxygen atoms because of this partial negative charge, and the rule states that if we have a trigonal planar molecule and all domains are the same, which in this case they are, the molecule will be non-polar. So SO3 is non-polar. Next we have OF2. I have calculated that there are 20 valence electrons, but let's check my work just to be sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 pairs gives us the 20 valence electrons we were looking for, and all of our atoms have octets, so that is correct. The central oxygen atom has 4 domains, 1, 2, 3, 4, 2 of which are non-bonding. So our domain geometry will be tetrahedral, but our molecular geometry will be bent with 2 non-bonding pairs and bonds to each fluorine atom. The 2 fluorine atoms will each have a partial negative charge, and the dipole will move towards the fluorine atoms. The rule states that if we have a bent molecule, the dipoles will not cancel, and we will have a net dipole in this direction. So this molecule will be polar. Next we have BeCl2. I have calculated there are 16 valence electrons. We will check that. 1, 2, 3, 4, 5, 6, 7, 8. 8 pairs, 2 electrons per pair, means that we have drawn this Lewis structure correctly. The central Be atom does not have to have an octet. We see that Be has 2 domains here, and they are both equal. That means we will have a linear molecular geometry. The Be atom will have a partial positive charge, and the two chlorine atoms will have partial negative charges. And the dipoles will move in opposite directions, and both the dipoles are equal. The rule states that if we have a linear molecule and both the domains are the same, it will be non-polar. Now to CCl4, there are 32 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pairs. Gives us 32 valence electrons. All of our outside atoms have octets, and so does our central carbon atom. The central carbon atom has 4 domains, all of which are equal, and there are no non-bonding pairs. That's going to give us a tetrahedral molecular geometry. The outside chlorine atoms will all have partial negative charges, and the central carbon atom will have a partial positive charge. The dipoles will move towards the outside chlorine atoms, and the rule states that if we have a tetrahedral molecule as its molecular geometry and all of the outside atoms are the same, the molecule will be non-polar. Now to our last molecule, which is O3, or ozone. Calculated that there should be 18 valence electrons in this molecule. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pairs of electrons, 18 valence electrons. But wait, we need to get an octet on this central oxygen atom. That is done because this molecule exhibits resonance, and there will be equal 1.5 bonds going to the central atom from both outside oxygen atoms. We can see now that the central atom will have 3 domains, 1, 2, 3, one of which is a non-bonding domain. So our domain geometry will be trigonal planar, but our molecular geometry would be bent. The central atom would have a partial positive charge because of this pair of non-bonding electrons, and the rule states that if we have a bent molecule, it will be polar. So our last molecule is polar. The question asks us how many of the following molecules are polar. Let's count. 1, 2. So our answer is 2 polar molecules, which are OF2 and O3. Some common mistakes that people commonly make is that they use the domain geometry to determine the polarity of the molecule, but it is very important to use the molecular geometry and not the domain geometry. Another common mistake that is made is people will just look at ozone, or O3, and automatically assume that since they all have the same electronegativity, that there will be no overall net dipole, but that is false, as we just saw. It is very important to draw the correct Lewis structure and the molecular geometry.